All right, let's see if that. Yes, that's fine. We'll give them a second. Yeah.
What is it called?
A screenshot.
Okay. Okay, it doesn't get bigger than that. Does that work for you, Rory?
Yeah, that's fine. Thanks. What's that? It's about 10 minutes. Yeah.
So you'll keep an eye on the time? Yeah. Okay. I'll set that. I can set a timer. Yeah, I will. I think sounds good. So it's 20 and then it will be 12. Correct. Yeah. 20 plus 5 minutes question and then 12 plus 3. Okay, that's it. Yeah, of course. Where is it? Oh, he's sharing the phone. Oh, yeah, I see him. Yeah. Great.
All right, we're gonna, before we get started, one or two more announcements for tonight. Our last social event of the week is Astro on Tap, which will be at Guilford Hall. Guilford Hall is a great brewery, German style, about 10 minutes from here. I don't think we're providing shuttle transportation, so you'll have to find a carpool or Uber. It's upstairs, typically. I assume that's where it's gonna be tonight. There's tables. Get a table with your closest friends. You can order dinner, you can order drinks. And I think the talks start at 7:30. And all the talks will be, I think, from conference attendees. I'm having a hard time finding the list. If you're giving the Astro on Tap, there's Matt. So everyone raise your hand if you're giving the talk tonight. And, and Nico too. Okay, so come out, support your peers. It's gonna be a lot of fun. And also, I believe somebody from the Roman Science Collaboration was planning a pre-meeting party about, you are, okay, perfect. Do you want to announce that real quickly?
I think there are people who are in the Roman Science Collaboration and thinking about advocacy for Roman on the federal budget level. We're maybe going to meet up around an hour or so before Astronomy on Tap at the venue to get together and talk through some strategy and ideas for advocacy coming up this fall.
All right, thank you.
Thanks, Ori. Welcome back. This is our second galaxy clustering session. Our first presenter today is Martin Croce. He will tell us about the recent news from Energy survey. Please, Martin.
Thank you. Okay, so thanks to the organizer for this wonderful meeting, very exciting so far. So I'm Martin Croce from the Institute of Space Science in Barcelona, and I will be talking about different cosmological analysis using the final data set, the dark energy survey from 6 years of observations. I will be focusing mostly on the combination of weak lensing and galaxy clustering, which is a lot of relevance for Roman and for Euclid, but I'll touch also on BAO and supernova, okay? All right, so by now probably many of you know that DES is an imaging survey using five bands in the optical and near infrared, GRI, and Z, The camera DCAM is in the south in the Blanco telescope. And DES observed for over almost 6 years, okay? Observations actually finished in 2019. And yes, we're still analyzing data. So this talk, as I said, is going to focus mostly on the ESCR6. The ES is basically covering 2 fields. So it's a wide5,000 square degrees to a depth of 24 magnitudes. And then, so basically, by the end of the survey, every line of sight in the sky is visited around 10 times, okay, to reach this depth. And then there are supernova fields, much smaller size, 30 square degrees, that are about 2 magnitudes deeper, okay? Those are visited over 100 times. So that is the survey. This is the science. The cosmology in DES comes in 4 flavors, if you want. So we do weak lensing, weak gravitational lensing, because we were able to measure roughly 200 million shapes of galaxies, okay? So all in red are actual final numbers on the catalogs already. We are also measuring baryon acoustic oscillations as a function of redshift from 16 million red galaxies this time, okay? We also measure galaxy clusters that are identified in the optical, 20,000 red mapped clusters, and then you can estimate their masses using weak lensing profiles or using scaling relations from SC and X-rays from other overlapping missions in the same area. And then the final thing, today's cosmology, is the use of type 1a supernova, okay? Which in DES have been super successful. And we have developed a new method to identify supernova photometrically. And that I'll talk about at the end, okay? Now, all these different proofs in a single instrument, single reduction, if you want, single footprint, with a lot of synergy. So DES is ideal to exploit the synergies between all these proofs. Okay? And this is how things came to be up to 2025. So first data came up in 2015, which is more or less when I showed DES. This is the science verification data. It was only 150 square degrees, but already then we were able to measure galaxy clustering, weak lensing, only 3-something billion galaxies. And back then, weak lensing was a growing field, okay? So it was very exciting. A few years later, we were able to do our first cosmological analysis with 1/4 of the survey, so 1,000 square degrees, 1.3, 35 million galaxies, okay? So 1/4 of the full area. 4 years later, the full area, not to full depth, already 100 million galaxy shapes. So that for the community is quite remarkable, okay? And in 2025, I swear we will have the analysis of the full area to full depth, okay? And this is a first thing that I wanted to notice here, which has, I guess, impact for the future, which is there are 4 years in between each analysis. Even though the pipelines have been growing, are more and more robust, all the analysis strategy are being set, and so on. So there are 4 years in every from analysis to analysis. So these weak lensing analyses are actually quite complicated. Okay? And how this is going to fit in the future with the space proofs that have a very tight schedule, it's something that is TBD. Okay. So as I said, BAO supernova are finalized, are on the archive. 3x2 clusters will come up this year or early next year. What we call DR2, it's public as well, the full images and everything, and the gold catalog was released earlier this year. Over almost 550 million galaxies and 150 million stars. Okay, and these are things that I think I'll mention before. Okay, let me jump into 3x2. Well, what do I mean by that? The combination of lensing and clustering. And you've seen this picture before, even in this conference. So we have a catalog of sources that we call it, for which we measure ellipticities, and we can measure the cross correlation of the ellipticities for galaxy shapes. That is directly proportional to the growth of a structure. Amazing. So you can measure, by measuring cosmic shear, the 2-point correlation, you can directly access the growth of a structure. And you can put constraints on sigma 8 and on omega matter as well from the shape of this 2-point correlation. On the other hand, you also have a catalog with positions. Okay, so you can measure the position-position correlation function. Unfortunately, there's a bias. That's a bias tracers of the growth of a structure, okay, which is known for a long time. This signal has a high signal to noise, so it's something easy to measure, but you have to get rid of this bias. And to do that, you use the cross correlation of shape and galaxy positions, which is what we call galaxy-galaxy lensing. So combining clustering and galaxy-galaxy lensing, you can solve for bias, so you can also access cosmology and the growth of a structure. And you can also combine the three things, and that is what we call 3 times 2. Okay? It's a way of accessing cosmology. 3 times 2, this is math 101, so what can go wrong? All right? And many things can go wrong. So we have in DS, we have 4 tomographic beams for the sources, okay? The ellipticity is a spin 2 field, so you can measure 2 2-point correlations per tomographic beam. So here alone, we have 20 2-point correlations. Galaxy clustering, we only measure the autocorrelation, so we have 6. Galaxy-galaxy lensing, correlating these two, is 24 2-point correlations. So in total, we have 50 2-point correlations that go from redshift 0 to 2, and from 3 to 100 Arc minutes. Now, all these 2-point correlations suffer to one degree or another by observational systematics and by astrophysics systematics that also depend on redshift and on scale. And all these 2-point correlations are correlated. Why not? Okay. And just to finish, you need photometric redshift to characterize all this, which is a field on itself. Okay, it's like an elephant in the room. It's quite complicated. In particular for the DES, which only has 4 bands. So yes, this can become reaching a point in which all these 2-point correlations fall in place and everything is self-consistent, and all the parameters that you need to materialize in this exercise has their own meaningful value. It's a quite complex exercise, and yeah, all this to say that's why we haven't unblinded yet. Okay. But that's the intro to 3 times 2. At least I'll show you what we got 4 years ago. And this is what weak lensing surveys measure, okay? It's a combination of growth of the structure and omega matter. So it's S8, this parameter S8 that you see here in gray. So in blue here is the growth of a structure and omega matter from cosmic shear only. The orange is from what we call 2 times 2, clustering and galaxy-galaxy lensing, and in gray is the result from 3 times 2. And Planck is over here. Okay, so in DES there is no tension with Planck; it's more or less one sigma away. And currently, stage 3 measures this parameter to about 2%. S8 is measured to about 2%. In stage 4, this will be measured to a sub-percent level. And this is still state of the art. More or less, is at the same level as Kidd's legacy is measured in S8, but only with shear only in that case. Okay. All right, so let me jump to DESI-R6 now. Let me describe a little bit so what I try to do is to describe different ingredients that go into this 3 times 2. Okay, starting from the samples, the simulations that you need, the methodology, and what do we expect. So the samples, the source sample was, which is a sample for which we measure shapes, was described by Massa 2 days ago very well. So we use this meta detection algorithm. There is a version of meta calibration in which you shear images and you measure the response of your shear method, shear algorithm, and to that change in the ellipticity. And by inverting that process, you can measure the galaxy shears. And as Massa was So this is meta-detect. It's an advancement of metacalibration in that it introduces shear biases, particularly in crowded regions, where you have blended objects. And Massa was showing that our shear calibration is to below order of 1%, which is what you will need for LSST year 1. The DESI year 6 is deeper than the previous than the DESI year 3, as I said before. So we have 50% more sources. Okay, so 150 million galaxies. The lens sample, on the other hand, is very different from the source sample. The lens sample, as I said before, clustering is a high signal-to-noise measurement, so you can allow yourself to play a little bit and select brighter galaxies that have typically worse shot noise but better photo-sees. So you can play this game. Okay, I select the brightest sample possible such that I'm not dominated by shot noise, and this is what we call this MACLIM sample. You can also select reg samples, which is red magic down here, which also would work well. Okay, and these are the redshift distributions that you get. Okay, the sources are typically fainter, so they go to higher redshift. The lenses are typically brighter. The redshift distributions are tighter. So the lenses are more sensitive to the width of the redshift distributions. The sources are more sensitive to the peak of the redshift distributions. Given that Massa already discussed a lot this, the source sample, the meta-detect sample, sorry, I'll focus on 1 or 2 slides in the MACLIM sample. Okay, so this time around, MACLIM sample is defined as a magnitude cut, basically, that depends on redshift. So galaxies are brighter at low redshift and fainter at high redshift, but it's basically a magnitude cut. This time around, we improve our quality cuts using self-organizing maps to being able to isolate quasars and stars. We also map our galaxies to the near-infrared photometry from UNWISE to complement the morphological star-galaxy separation flags. So we have done quite a better job at separating stars from galaxies. In particular, in low latitude regions, close to the our galaxy, okay? So this is in terms of sample selection or sample curation. The one thing that is very, very important for galaxy clustering, that is critical, is, that would be the equivalent of the shear calibration, let's say, is mitigating large-scale observation and systematics, okay? So that is the one thing that is very important. And what this is that when you observe, it's a function of time, the observing conditions change, okay? And this induces large-scale fluctuations in your selection functions, okay? So the air mass, everything changes and introduces large-scale fluctuations in your selection function that are mapped, that are physical, right? And since galaxy clustering is about measuring galaxy density fluctuations, you have to be able to measure the mean density very well. So you have to map out these fake fluctuations from your sample. In DES, the way in which we do that is by storing internally all these observing conditions as a function of the observing time. So we not only store the galaxy position and so on, but also maps for what was the scene, the air mass, the depth, the sky brightness, and so on. In addition to external maps like stellar density or dust. And we have 2 methods to map out these phase fluctuations, which you can see here, right? So what these panels are showing is the number density of galaxies as a function of dust, stars, and the depth in the WISE photometry. And you see that there is this trend here that it shouldn't exist because our sample should not be correlated with astrophysics. So one of these methods, what it does is using MOX, is to find what is the most relevant of these trends, and it applies weights, and then it reevaluates all these plots again and applied other weights to the second most relevant case, and so on, iteratively, until you remove all of these trends. Okay? And this is a method that is well known. Actually, has worked on this for a long time. It's one of the developers of this kind of method. The other method is, but this goes one by one. So it's an iterative process and requires MOX, and it's quite slow. The other method that we use is just a linear regression using all maps at once. Which obtains the same result. It's just weights. And what you see here is, given that the photometry now, after 6 years of observation, is so uniform, okay? This is the size of our corrections by observational systematics. So what the blue is showing here is in MOX, the result of contaminating MOX and correcting by this method or not. So this is, in blue, is the size of our actual, well, no, it's not in MOX, this is in data. So it's the raw clustering minus the clustering after you apply these weights. So this is a blind quantity, it's just a difference. It's the raw clustering minus the clustering after applying the weights. And you see the size of corrections in blue compared to the error bars. So it's well within the error bars. At all redshift except at the last one, where things go a bit more crazy, okay? And the two methods agree very well to each other. And we marginalize over the difference, okay? So all this to say that we control, we think we control these observational systematics to a good degree, okay? That's all for data. Let me jump to simulations now. These are the 3 types of simulations that you need to be able to do this weak lensing exercise, or at least that we need. Varrock is the first one. It's basically Varrock is a synthetic source injection algorithm of objects, or typically galaxies, from the deep field into the pixel level wide field images. Okay, so in the DESI images, you inject galaxies from the deep field, and after you do that, you run all the reduction algorithms. You can generate co-added images. You can generate catalogs. You can measure meta detect again, MACLIM again, and so on. And Varrock is truly, truly critical for us, in particular, to calibrate photometric redshift, to being able to map the wide server to the deep server. I'll tell you more about that in a second. We also measure lens magnification, which is important, very important, star galaxy separation, and other systematics using Varrock. And this code by now is so streamlined that for the first time we were able to run all these source injections in an area equal to the full footprint. So we run twice the server if you want, okay? With over 150 million injections. That's Varrock. The image simulation, I think Masa was talking a little bit about this as well. This is basically putting galaxy stamps on images that have the DES configuration. And these stamps have a known shear. So you can calibrate your shear algorithm. You can calibrate your biases. And because you also run photo-sys on those simulations, you can you can calibrate these biases as a function of time. Okay, and then cardinal disembodied simulations. Okay, so let me jump over photometric redshift, and I can talk about that in the corridor if you want. These are the analysis choices for the DESI-R6. We do use scale cuts, which is something that we discussed in the past. We have minimal scales of 9 arminets to 3 arminets and 13 for W theta. The one thing that I wanted to bring up here, which is very important, is that so our scale cuts are set in such a way that you don't generate biases of more than 0.5 sigma in the parameters that we constrain. In terms of the inference, for unblinding, the one thing that is critical that I wanted to mention is that we have to marginalize over 50 parameters, something that Agnes mentioned at the beginning as well. And this requires, in total, several million CPU hours of computing time, okay? And this is yet something to keep in mind for the future. How do we bring this down to be able to run chains in less than 1 day? Okay, let me show you what we expect for the DESI-R6 in terms of constraints. These are the galaxy lensing, galaxy lensing, and cosmic shear signals that I mentioned at the beginning. These are now forecasts, okay, of what we expect. So combining 1 times 2 and 2 times 2, those are the figure of merit. The combination of both doubles basically the figure of merit, which is something we knew from year 3. So really, it's very, very worth it to do this exercise to double your figure of merit. And also 3 times 2 in general is very robust to systematics in general. And in terms of actual constraints for parameters, we expect to see further 30% improvements in omega matter and sigma. Okay? Okay. Let me mention in 1 minute. So the supernova that I mentioned very early on, in DES we have been able to classify supernovas photometrically, which is critical not only to access high redshift, which you cannot if you do it spectroscopically, and also to avoid biases, selection biases at high redshift. The VAO measurements in DES is as well photometric, of course. It's a detection of almost 3.5 sigma. Here is a little bit discordant with Planck. And then both supernova and VAO are proof of expansion history. So you can combine them both. And what you get is this plot. In terms of VAO and supernova are 2 or 3 sigma tensions in lambda CDM. So if you open lambda CDM to W0, WA CDM, then everything falls into place, and you find basically a 3.2 sigma discrepancy with lambda CDM from combining DES VAO and DES supernova, which is not far from what you find with DESI DR1, which is order 3.9 sigma. Okay. So already DES data combined with CMB, which is something I didn't mention, is showing this tension from, or this preference at this 3 sigma something for dynamical dark energy. Okay, and to finish, clusters, I was not planning to talk because Changhao mentioned clusters, was discussing clusters on Monday. And then this is a summary. DES has trained, I think the most important contribution from DES for me is the amount of people that has trained for stage 4. Maybe 60 people I can count that are still active in the field and that I'm sure will lead science of stage 4 surveys, in addition to infrastructure and methodology. So I think this is the most remarkable thing for me. And this is just a result from the SVAO, from supernova, from 3 times 2 that we expect to unblind in a couple of weeks, so stay tuned. And after these 3, then we combine everything to finish this for once. Okay, thank you.
Time for a few questions, if there are any questions in the audience. One online? Yes. You can ask your question. I don't know.
Question online here. Would it not make sense, as per earlier talk, to include Z in the galaxy clustering measure?
You mean in the labels and stuff?
Z, the redshift, right? Yes, the redshift.
Okay, yeah. Yes, definitely. It's not C. These measurements are done in tomographic beam, so you will have to include to which tomographic beam. But yes, it's a redshift dependent.
John?
So you showed how to mitigate the imaging systematics. So how do you ensure there's you can avoid overcorrection?
Yeah, what we do is we imprint these systematics in MOX, and we run the pipeline in MOX. And yes, the caveat is that in MOX we can only imprint the systematics that we know exist. We don't know what we don't know. But something else that we can do now that I think is super cool is that using Barrock, in Barrock traces the dependence with observed conditions super well. So I don't know if you noticed. For example, the upper polos there. So So we can run the mitigation pipelines in Barrock, and there we can check that you're correct. Yeah.
You do calibrate the overcorrection and marginalize it out.
Yes, exactly.
In Y3 senses.
Yes. Yeah, the overcorrection is typically very small in year 6.
And let's have one more question. Yes.
Hi. I had a question about the Maglin and the red mappler.
Red magic.
Red magic sample. So in DESI there was some discrepancy, if I remember right, between using them for clustering. Was that a choice for using Maglin only for the results?
Yes, in year 3, there was a selection effect in red magic that we realized at the very end. And that's why we used Maglin for year 3. Then we understood what the selection effect was, and we corrected for it. So right now, we could be using any of the two. It's just a question of practicality that we're using. We are developing the 2 of them, but one of them is more advanced than the other. But there is, now we understand both of them.
Okay, thank you very much, Martin. And our next presentation is by Jacqueline McLeary. She will tell us how to deal with the dust. Please, Jacqueline.
Hello, everyone. I'm Jacqueline McLeary, and I'm here to share some results with you that were finalized in March and consider the relevance to some of the science going on with Roman. So this project is, like so many of our projects, the team. Eric Huff, my former postdoc advisor at JPL, came up with the original idea. Jim Bartlett, Brandon Hensley, both dust experts in different areas, and I did a lot of the development and analysis. So there were early hints of megaparsec scale dust around galaxies. One of the most dramatic results came in 2010 with a paper led by Bruce Menard et al. That found a nice smooth profile of extinction that they attributed to circumgalactic dust halos, visible out to 10 megaparsecs, with an amplitude of, we'll come back to this, but an amplitude of 4.4 10 to the minus 3 mags, and a slope around minus 0.8, 0.9. This is, of course, not the only result. In the interim, there have been many more studies of circumgalactic and intergalactic dust, mostly with magnesium-2 equivalent widths. And one of the findings that at least surprised me when I first started getting into this is that there are gigantic dust halos around not just star-forming galaxies you might expect, but also luminous red galaxies as well. My Astro 101 take a thought was like, there's no ISM and elliptical, so they don't have any dust either. But this is evidence to the contrary. And there have been many papers since then as well. Oh, sorry. Okay. Hopefully everyone could hear me anyway, but now it'll be a little easier. So the Stardust team, including myself, decided to come at this, I don't know if you want to call it a problem or interesting astrophysics from an entirely different perspective, maximum likelihood estimators. So as most of you in the audience know far better than I, a maximum likelihood estimator is something that you can construct to find a set of parameters that maximize the likelihood of having observed your data set if you know the fundamental underlying model for your data, for your statistical distribution. This is very common in cosmology. And Eric Huff's idea was to set up these standard likelihoods that log likelihoods that we've all seen, but instead of, I don't know, galaxy shears or shapes or what have you, the model that we'd be using is galaxy colors, which if you Taylor expand, you get, so measured galaxy colors is an intrinsic galaxy color M0 plus rho, which in this case is some unit dust, some unit AV, times a theoretical extinction curve. So how a given AV of dust changes the magnitudes of your observations at a given wavelength, at a given bandpass. So mathemagic, you end up with a nice estimator for this AV, rho hat. And something worth pointing out is that this model that we've established is entirely generic. D can be, the data vector can be any photometric data set. You've got magnitudes, you can plug this in. And the theoretical dust model, dm d rho, can be any extinction model for dust that you want. So one of the Gordon et al. 2023, SMC dust, LMC dust, a particular grain model, what have you. All of these things can be plugged in. We've heard a lot about 3x2 point statistics, but you don't just have to correlate positions and shears. You can also correlate foreground galaxy positions with background galaxy colors. So the next step was to construct a two-point statistic, a two-point angular correlation function, correlating galaxy positions and background galaxy excess reddening, where excess reddening means subtracting away the mean color of the galaxy population. So what you're left with is a differential reddening, an excess reddening, if you will. And then, of course, like in all of these analyses, you have to account for the contributions of random foregrounds, random backgrounds, add back in the contribution of random foreground times random background, and so on. But it's a relatively simple idea. We are looking for cosmological scale, megaparsec scale dust halos by cross-correlating the presence of a foreground galaxy with dust-induced reddening of background galaxies as probed by the maximum likelihood estimator that the Stardust team and I set up. Our initial results were based on two catalogs, a background sample culled from the Dark Energy Survey's Red Magic catalog, which we just heard a lot about, and then a foreground sample drawn from the WISE-X WISE by Supercosmos dataset, as well as a low redshift subset of red magic galaxies. The WISE by Supercosmos sample I chose because it's all sky. It has well-constrained photometric redshifts, high purity, and so it lends itself not just to use with red magic, but use with any other number of background catalogs. So the final number of foreground galaxies was about 1.3 million at a mean redshift of 0.1. I'll bypass the details of red magic because we just heard about it, but the background galaxy sample that we used was drawn from red magic because it's got a very tight dispersion in color. If you're trying to find an excess reddening, a difference in color, it helps if the underlying sample that you are using does not have a wide variance in color. It's just easier to measure the signal. Okay, I'm doing good on time. So putting all of this machinery together, putting all of these results together, what did we find? A beautiful confirmation of this early result by Menard et al. In extinction and magnesium-2 equivalent with absorption studies that came afterwards. The red line here is the power law found by Menard et al. In 2010, and the luminous red galaxy extinction profile is shown here in as dark red points. The foreground sample that we used was a low redshift subset of the Red Magic catalog to ensure a decent foreground-background separation. And we found extinction out to 40 megaparsecs. So essentially, as far as we could measure it, there was signal of dust. A slope of about 0.8, similar to basically all of the literature, which suggests that dust perfuses the halo of the galaxy. And then, we already saw this plot, but now paying attention to the blue points, which is the cross-correlation of the WISE by Supercosmos catalog with the two Red Magic catalogs. We detect extinction again out to 1 megaparsec, but with a few differences from the LRG profile. One, a steep rise in the extinction lower than 50 megaparsecs, which I interpreted as the presence of lots of dust in the CGM of galaxies that presumably comprise both star-forming and quiescent, and then a roll-off at about 1 megaparsec. I don't need to belabor the details of this surface dust conversion that Brandon Hensley came up with, but it's just a little easier to see on this plot. So the LRG, luminous red galaxy extinction profile, goes out pretty far, is kind of flat. The mixed quiescent and star-forming sample has a rise in the inner CGM, a rise representing the inner CGM, and then same slope in the 1 halo term, and then a fall off towards the 2 halo term. This is really cool. I wanted to make sure that I was not dealing with any sort of systematics, so I implemented a few simple tests, replaced the foreground catalog with stars, repeat measurement, replace the background catalog with stars, repeat the measurement, and invert the foreground and background. All of these things should yield null results, and they all did. In fact, the amplitude of the slope and coefficient is like 10,000 times lower than what we actually found. So I was pretty confident in the result. We applied cosmological methods, borrowed cosmological methods to study the CGM and really the IGM at 40 megaparsecs. And now we go back to cosmology. So again, as many in the audience know far better than I do, supernovae and distance measurements to supernovae are affected by all sorts of dust. Host dust, progenitor dust, galactic Milky Way extinction, and everything that lies between the Milky Way and the supernova, all of that dust. It reddens supernovae, confusing, adding some scattered distance estimates. And while we have a pretty decent handle on galactic extinction, and there are lots of very clever folks working on modeling the intrinsic dust of the progenitors and the host galaxies, what do we do about this intergalactic dust? Is there some way that we can mitigate it a little bit better? So a chat with Now Suzuki in the audience, hi Now, gave us the idea that this technique that we've established, this model that we've established, could theoretically be used to correct supernovae for intergalactic dust on a supernova by supernova measurement based on the impact parameter and type of galaxy, sort of in the field of view, if you will, to your supernova. So these arrows are just schematics representing this. While we might expect this to be a small effect, after all, the extinction that I found in these curves here is a part in 1,000, a part in 10,000, 0.1 at the lowest impact parameters. The high latitude time domain survey is going, as last I checked, is going to yield 27,000 supernovae, 10 times more than all previous supernovae combined. Little systematic effects that were once buried in noise are all of a sudden going to become a lot more important. So I argue, again, based on Now's very clever idea, that we now have the means to do this correction piece by piece. I'm over time, but a couple of considerations as well is that the cosmic abundance of dust is not constant with time. It peaks at about a redshift of 1 and then tapers off. Theoretical findings by my collaborator, Brianne McDonough, confirm this. And then I don't think that the spatial distribution of dust is a uniform screen. This is a visualization of neutral hydrogen in TNG 300 prepared by Brianne in the audience. And neutral hydrogen follows the cosmic web. If dust follows neutral hydrogen, then it stands to reason that you are not looking through a uniform screen of dust. This needs to be taken into account as well. So, summary, new evidence for megaparsec scale halos with real differences between star forming and quiescent samples. I think that it's time to apply this machinery to Roman, the Roman supernova survey, and we have a couple of calibrations and CGM, IGM dust investigations planned based on a collaboration with Brianne McDonough, a theoretical hydrosims expert. And with that, I'll take questions.
That's right. So is there anything about the method that can kind of distinguish between smooth dust in a CGM versus like dust in satellites and like dust in other galaxies whose position is correlated with your foreground galaxies?
So if I'm understanding correctly, you're saying, is there any way that we could tease apart satellite dust from diffuse CGM dust or IGM dust?
You were using terms like dust halos, but it wasn't clear to me that this couldn't just be dust. Like dust only lives on small scales around the centers of galaxies, but other galaxies lie around these galaxies, and so I get this signal on average.
Well, just based on a volume filling factor, satellites don't comprise enough of that 100 kiloparsec scale halo to account for the entire dust content that we measure. That, based on a conversation with Brianne, that dust gets stripped away preferentially from the CGM of little satellite galaxies as they fall in, but their volume is small. It can't explain everything. And certainly by the time you get out to 40 megaparsecs, that's not an individual galaxy halo, but presumably the overlap of many galaxies.
Maybe a different question, like, is this a surprise if you take like a hydro simulation and assume something about how like dust traces the metals in gas or something? Is this result expected, or is this?
We're working on that. Brianne probably has more comment than I do, but I don't think it's a surprise.
Jeff?
Yeah, Jeff Newman, University of Pittsburgh. Just following up on that, if you look at the difference between the clustering effectively of the dust around the blue galaxies and the red galaxies, that is the signature you would expect if you're actually seeing the effects of dust in other galaxies at 3, 4, 5, 10 megaparsecs, because those galaxies cluster more with the red galaxies.
That's right.
So I think that's very much a scenario we're thinking about.
Excuse me, could you say that again?
So I think that's very much a scenario we're thinking about.
Yeah.
That this really is dust from other galaxies, and possibly the only part that's really sort of a one halo, one galaxy part of what you're seeing is actually that in the blue galaxies at small scales, and you're just seeing the effects of other galaxies.
I think so. There's this tired wind model for dust outflows that suggests that lots of material leaves galaxy disks and hangs out at actually about the distances that we see, sort of accumulates over time, maybe gets self-shielded within the neutral hydrogen of large-scale structure, and so persists for a long time, persists for billions of years rather than hundreds of millions.
I think even without that, if dust is local to galaxies, if all the dust is within 100 kiloparsecs of a galaxy, you would see a decline with scale just due to the clustering.
Yeah,
sure. It may be worth checking the relative bias of your red and blue samples, their autocorrelation. Because if the scaling of the dust actually is scaling with the relative correlation of those, that does suggest it's sort of a two halo effect.
Sure.
As opposed to a link.
So this is actually one of the theoretical investigations that I'm planning with Brianne McDonough based on hydrosims. One of the questions that she's interested in is, where is this dust? Is it just in one halo term? Is it embedded in large-scale structure? And illustrious TNG 300, I think, gives us the tools to answer this.
Great.
So we had one question and then one question from Dominic.
Hi, I'm Sangeeta Malhotra. Very quickly, can you estimate sort of dispersion or the clumpiness of the occurrence of dust? Get a mean value as a quantity. How much does it scatter? And that may give you some estimate whether it's smoothly distributed or not.
I don't have a good intuition for that.
Okay, let's not.
Yeah, sure.
So I was glad to see you show the sort of mean relation of AV to neutral hydrogen density. How are you inferring the hydrogen? Is it like from distribution of column densities in Lyman alpha forest, or what? Where are you getting?
So then this neutral hydrogen plot here,
Okay.
sorry, this one?
Well, that may be the answer. You were, in a previous slide, you had actually shown, value of AV over NH.
Oh, yes, yes, yes. Oh, I passed it already.
Yeah.
Yeah, here. So this conversion was based on this astrodust plus PAW model conceived by my collaborator Brandon Hensley and Tim Drain, published in a 2023 paper. So their astrodust is sort of like a generic dust grain model, and they assume a dust surface density of whatever that is, 1.18, 10 to the 26 grams per neutral hydrogen, and then an extinction per hydrogen column density shown here.
Okay, that's just different from, not surprisingly, from the ISM, but I was the Milky Way ISM. But
yeah, and
this is fascinating, actually.
The surface dust mass idea.
Well, just the whole question of really looking for. I used to do, absorption line studies to measure abundances of gases, and dust was always just an incredible nuisance. So it's fascinating to see. You actually do see dust out from such large distances. That's really cool.
I'm afraid we will have to move this discussion to lunchtime. Thank you very much, Jacqueline. And our next presentation is by Taehyun Shen. Mining Rubin and Roman photometries.
Hi, thanks. I'm Taehyun. I came at a perfect timing because I only have 8 slides. So I'm gonna today talk about our project under Roman High Latitude Imaging Survey team. This is just an exploratory study, not representing the whole team's plan forward. So I just wanted to make sure that first. So everyone at this point has the same idea, Roman Strait and Rubin Strait, and we should combine them. So this is our attempt to do that. So the goal of this project is to first performance test of LSST science pipelines to process Roman income collated images, to process them on the same platform to see how things improve, and so to evaluation of improvement in photometric performance when combining Roman data with Rubin. For example, our plan is to do the force photometry on Rubin using Roman to see how blending and position improves. And thirdly, impact on photometric redshift estimation when including Rubin into Roman. So this project is on Roman's perspective. And then as a stretch goal, if we could, we will estimate this impact on shape measurement. But we're still on the goal, the first stage, the photometric analysis. So this talk is just to introduce our plan and show you a very preliminary result on our photometry result with LSP. So to compare Roman with Rubin, there's 3 aspects I want to highlight: photo Z, deblending, and thirdly position. Maybe not too important. So for photo Z, Rubin adds crucial coverage at low redshift to Roman, and then while Roman complements Rubin by adding rest frame optical images at high Z, especially redshift larger than 1.5. So for example, I overplotted the typical passive galaxies, red galaxies here as a function of redshift, 0.512. And then you can see that the most important feature, the Balmer break at 4,000 angstrom, that above redshift 1.5, it goes into the infrared band. So the Raman image at this redshift is very important for having redshift, and vice versa. The optical Rubin band information is very important for Raman galaxies to have credible photo-Z values for low redshift galaxies. And then also to be able to fully exploit the Rubin images and Rubin photometry to Raman, we need to have the joint catalog, but one way that Raman can help Rubin so that we can exploit Rubin better into Raman is that Raman can deblend majority of unrecognized blends in Rubin at I magnitude greater than 25, as in Troxel 23, and very recently, last week, the Rubin published this Anya Adari and von der Linden as a tech note, where they show that 18% of their data preview 1 image galaxies are unrecognized blends. And then we can also, Raman have better flux and better shape from better position, talking about 10 milliarc second versus 1 milliarc second. But here on the right-hand side, I show schematic diagram of the pixel size of Rubin, Raman IMCOM, the co-editing algorithm our group has developed, and then also the rough get galaxy size under PSF. So this Raman image is great sharp here, red box, like 0.11 arc second per pixel, but their PSF size is about their pixel size, so their PSF is undersampled, which is a big problem in weak lensing shape measurement. So the point of IMCOM is to reduce the pixel size and then increase the PSF size a little bit to have the oversampled PSF. So now the PSF size, the full width half maximum, is 6 times the pixel size. So we're good. So I'm gonna focus on the IMCOM images of Raman when we talk about the raw Raman images, and that's that's the output target PSF, the Gaussian PSF. So that's what I'm gonna use. And then I'm gonna use the Open Universe 2024 simulation, which is about 70 square degrees of Rubin and Raman image simulation. They have improved extragalactic model, deep sky, that Andrew talked about in the first day, and then transient model and improved survey telescope, and overall improved simulation realism. And then we have 1 square degree of IMCOM co-eds, subset of the whole simulation. And then this is the example image from Troxel 2023. And then we can, the link is here. So I'm gonna use this Open Universe simulation to test our for our analysis, and then also the LSST science pipelines. To briefly introduce, they say the LSST science pipelines are designed to enable optical and near-infrared astronomy in the big data era. So it basically has everything inside as a pipeline, configurable pipeline like ISR, image calibration, single frame processing, co-addition to all the final data products, and then it is used for LSST data preview 1 and easily applicable to other survey data. That's great. So we're going to use LSB to process Raman data for consistent photometric analysis of Rubin Raman images. So my analysis plan is like this. So for the photometry and deblending part, I'm gonna first do Raman YJ band photometry and Rubin 6-band photometry separately, and then matching to use it separately, not in a joint way. And then secondly, I'm our main analysis would be the detection on Roman H band, our reference band, and then do the force photometry on all the other bands here, and then to see how our photometry improves. And we're gonna also run a grid simulations to isolate the blending effect, how much blending is improved. And we are gonna compare this to other photometry algorithm, for example, NGMX plus multi-object fitting or source extractor and etc. To quantify improvement by using Roman photometry as a reference for Rubin combined photometry. But I want to highlight that this is not a fully joint photometry, but this is using Roman H band as a reference band to do force photometry on all the other bands. And then the photo Z, our baseline combination is Rubin Y1, Y10, UGRIZ plus Roman medium tier with the various data configuration from the last slide. And we're going to use Rail redshift assessment infrastructure layers. This is an open source software library providing tools to produce at-scale photometric redshift data product, including uncertainty and summary statistics, and stress test among the real systematics their webpage says. And this is initially designed as an infrastructure support for Rubin LSST, and then now it's applicable to general optical IR and whatever photometric survey. And then one great benefit of this platform is it already has numerous photo Z estimation algorithm implemented, like all you can think of, like BPZ, CMM, and everything. So it provides an optimal platform to test and validate photo Z analysis, including various surveys together. So this is my only result plot. So we are still on our photometry side, like in a very early stage. And then this is just to show that capability of LSP to process Roman images. So now this blue is star photometry, and then this magenta is the galaxy photometry. Star photometry is PSF photometry, and galaxy photometry is C model. Our star photometry looking good, but we still have to figure out why this 8% flux over estimation when we use C model for the galaxy fluxes. And these like 8%, the number is like is prevalent in all the bands. So we suspect this is some simple systematic that we can fix by one click or not. But we'll see how it improves. So to summarize my plan, we're gonna optimize the LSP photometry pipelines for processing Roman coads, and then we are gonna do force photometry of LSST images using Roman detection to generate a joint catalog for performance testing of Rubin Roman photometry and the photo Z, the improvement in photo Z performance by combining Rubin into Roman using Rail framework. And as a stretch plan, we'll see how it impacts on weak lensing shear measurements. Thank you.
Thanks. Are there any questions? Yes, please.
So yeah, thanks for the talk. There are similar discussion in the Rubin Euclid implementation, what direct data product implementation working group, and I was wondering if what you set up could be applied to Euclid easily, or if it's like very Roman specific.
I think like once we figure this out, I think the setup could be easily applied to other space telescope IR ground-based optical. But I think it's possible, but we'll see soon, I think. Yeah.
Thanks.
Well, thank you very much. Yeah, let's do one more question. There is a question in the audience.
I'm curious if you've got like a data management strategy in mind for transferring data and compute needed to do sort of, this type of work and that kind of thing?
Oh, I frankly have no idea and haven't thought about it at all. But I'm sure some people in our team have thought about it. So I'm sorry that I have no answer for that.
Okay. Okay. Thank you very much again. Our final presentation of the session is, this is final, right? Yes, by Shivam Pandey. This is a remote presentation. Shivam, can you share your screen, please? Through WebEx.
Can you see my screen?
Okay, good. Yeah, I can confirm that we can see it and we can hear you. So yes, please go ahead.
Okay, perfect. Thanks everyone for having me. I'm a postdoc across the street. However, I'm traveling, so I couldn't be there in person. So today I'll be talking about how to improve the cosmological constraints from shear 2-point correlation by adding an additional probe that effectively probe the baryonic physics and cross-correlate that with shear. So basically, the weak lensing that will be very exquisitely probed by Roman telescope probes the integrated total matter density, and by total matter density, it receives contribution from not just dark matter but also gas as well as stars. Now, as you all know, dark matter is much easier to simulate and understand its structure formation. However, the physics of gas is much more complicated, particularly these very high energy phenomena such as AGN feedback or supernovae complicate or like input so much energy that it impacts the distribution of these matter component even at megaparsec scales. Sorry, is there any issue on the slides?
No, we can still see your slides.
Okay, sorry. Yeah, so the issue comes here basically that in here, if I plot the power spectra of the total matter in some hydrosimulation relative to if I only had dark matter as my total matter component, you can see that different hydrosimulation that effectively implement different mechanism for these high energy feedback phenomena give us very different inference of how this matter power spectra looks like. And to see how relevant it is for Roman-like science, in this paper with Chinhao, what we tried doing was to forecast the constraints on this, the cosmological parameter space in this S8 omega matter space with Roman, and the expected constraints are, for example, in black. And then if we analyze that and if we have these kind of baryonic suppression, and if we analyze that simulated data vector without having this baryonic physics in there, we can see that we will expect more than 20 sigma biases in our cosmology. So the idea is, can we use some other probe that effectively probes the physics of baryons much more closely? And can we use that to understand how the total matter distribution is impacted? And the probe that we use here is the Synergies effect. And it comes because as the photons from the CMB travels towards our telescope, they get scattered by the intervening free electrons. And particularly if the scattering happens due to the random thermal motion of the free electrons, that generates this thermal DESI effect that changes the energy distribution of the photons. And we can use multi-frequency observations from CMB to extract out the properties of the thermodynamics of the electrons. And particularly what this thermal DESI probes is the integrated pressure along the line of sight. And now the idea is, can we use the fact that now we have a very good handle on what the thermodynamic of the baryons is, and can we use that to understand how exactly they are distributed and hence pin down the distribution of total matter. So to write it down in the halo model language, so the shear 2-point correlation that we are interested in is this can be dissected into one halo and two halo. And the one halo, if we write down the profile of total matter as rho dmb, we have this normal one halo contribution. And then if we have the shear cross DSZ, we now probe the pressure in the same halo. So the one halo is the distribution of density times pressure, and then we have the two halo contribution. Now these fields are very correlated, right? So we need some sort of connected model. And that's the thing that we came up with here, which basically enhances this traditional baryonification technique that was developed in, for example, in Schneider et al. Paper, and kind of consistently predicts what the pressure of the gas is. And not to go into too much detail, basically it takes it dissects the total matter distribution into its essential component, the gas part, the star part, and the dark matter part. And it says that you parameterize the gas part with some generalized NFW kind of profile, and that becomes your central free parameters. Because then what you can do is, once you have handle on the total density, you can say that I'm going to get the handle on the total mass within some given radius. I'm going to use the hydrostatic equilibrium condition to get the total pressure, but the thermal SZ is sourced by the thermal pressure, so we need some contribution from non-thermal support. And basically in that way, without having external free parameter that control the total pressure, we can consistently predict it from central set of free parameters. And that's the thing that that gets us both shear as well as thermal SZ. To see the power of this joint analysis, for example, in here, what I'm plotting is now the expected 2-point correlation as a function of angle. So now in real space, that will be expected from LSST-Y1, for example. And what these different color lines show is the predicted 2-point correlation when I change the strength of this baryonic feedback. And particularly to focus on the small scales, you can see that the strength of the feedback, or like the impact of feedback, is approximately similar to the measurement uncertainty. So you cannot use these small scale points to get constraints on cosmology, right? Because you'll have to marginalize over the feedback thing. What would really help if you can pin down which exact color line your universe has, so that you can use rest of the points to get cosmological constraints. And that's exactly the job of the cross correlation, because in here, if you do the shear cross DSZ, you can see the impact of feedback is much larger than expected measurement uncertainty. So this will pick out which color line your universe has, and then you can use all the points to get cosmological constraints. And that's exactly what you see in the Fisher forecast, that if you only analyze shear 2-point data, for example, on the left-hand side, the cosmological constraints are given in black. But when you jointly analyze the shear cross DSZ with red, you improve significantly. And the reason is because you improve much more in the astrophysical parameter constraints, and that breaks degeneracy and gives you tighter cosmological constraints. So we went ahead and did this thing in the current state of the art data, which was the DSER3 source distribution that Martin mentioned just now, and then we cross-correlated with the app DSC map. So the DS is having more than 100 million source galaxies, and we take the shapes of that spread over more than 4,000 square degrees, and we cross-correlate with this DSC map that has that can probe very small scale with 1.6 arc-minute beam. And we did all the usual observational systematics test. So here you see the measurement. So the 4 different panels show the cross correlation with 4 different tomographic bands of the source galaxies cross-correlated with the thermal SZ map. So this is to date the highest signal to noise cross correlation. And what's plotted with the solid line is the best fit from the model that I just mentioned, and you can see that it gives us a reasonably good best fit. This is a busy plot, but basically just to show that we get similarly good best fit with the shear 2-point correlation with all the tomographic bands and both psi plus and psi minus components. So let's now get to the results. So here I'm showing the parameter constraints. On the left-hand side, essentially the two main cosmological parameters, the S8 and omega matter, and one of the important baryonic parameter. And basically what this baryonic parameter does is it controls how the mass evolution of the gas ejection radius. So basically due to feedback, how far out the gas will be ejected and how exactly does it evolve with mass. And if this particular parameter is more negative, that means the gas is ejected more in lower mass halos. And this is exactly what we would expect because lower mass halos have a little bit shallower potential wells. So any high energy event will push out the gas more. So if we see in here, first let's see the cosmological constraints. If we analyze the probes individually, so shear 2-point only and shear cross DSZ, that's shown in red and blue. And then in the black, it's the joint constraints. So you can see that we improve the cosmological constraints significantly if we do the joint analysis rather than just shear 2-point. And another thing is you can see that our constraints on this new theta ejection parameter is has more weight towards the negative value. And on the right-hand side, we are comparing our constraints with external probes. And you can see that in the gray band or in the filled contours, we are showing the public DSY3 constraints that use that remove these small scales to not have to deal with these baryonic effects. But in black, because we now have model that can incorporate these baryonic effects, we get tighter constraints compared to the DS public, and we are more or less consistent with the CMB constraints from Planck and Planck plus aft. But we can go a step further. So because we now have the full parameter space, we can use that to get inferences on astrophysical quantities or cosmological quantities. So the first thing that we infer is the total matter power, or basically particularly what the total matter power spectra suppression looks like relative to prediction from dark matter only. And that's the thing that's given in the gray shaded region. And what we plot in different lines is the prediction from different hydrosimulation. And you can see that we kind of are more consistent with this Cosmo-Owl simulation that has a little bit more extreme feedback compared to, for example, Millennium TNG or Flamingo. And these are in tension at around 2 to 4 sigma level. And on the right-hand side, we are doing inference of this this correlation between the matter power suppression and the baryon fraction and 10 to the power 14 mass halos. And there was this nice paper, Wendell et al. 2019, that analyzed a bunch of different hydrosimulation and showed that these two quantities are very tightly correlated. And we can see that our inference falls is pretty consistent with the prediction there. And lastly, we can also infer this another quantity, the YM relation, which is the integrated TSZ, integrated thermal SZ, or the thermal energy as a function of halo mass. And again, you can see that our inference kind of is, you can see our inference compared to a bunch of different hydrosimulations. And you can see that our inference is consistent with this Cosmo-Owl simulation as before. And because that one has a little bit more extreme feedback relative to the other simulations. And particularly, you can see that it kind of predicts a little bit lower integrated thermal SZ in lower mass halos, which is consistent if you push out the gas outside of the halo boundary due to these high energy mechanisms. So yeah, I'll conclude here that we analyze the shear cross DSZ measurement with shear 2-point with this connected model, and we'll have another paper out on the archive hopefully later today or early next week that show that this is one of the most flexible and physically interpretable model compared to other alternatives. And we detect this increased baryonic feedback in lower mass halos. And I think like it's particularly exciting because with Roman and with SO coming out, these kind of multi-probe analysis will become really, really powerful, and we can do so much more. Thank you.
Very much. Shivam, are there any questions? Yes, I see a hand raised.
Oh, really nice work. I was curious if you go back a couple slides to your sensitivity plot of the feedback sort of a pivot at 1 arc minute. If you could walk through that and what the sensitivity is on the larger scales also. It was one of the colors for the feedback.
I couldn't hear it very well. Apologies.
We go back maybe 2 more slides. Oh, sorry. Keep to the sensitivity to feedback. Yeah, that one. I was wondering if you could walk through. So it seems to show a pivot of 1 arc minute. I was wondering if you could walk through that and also what's happening on the larger scales.
Oh yeah, sorry. So you mean approximate for the shear cross DSC one, right?
So on the shear cross shear side.
Shear cross shear side. Yeah, so I guess like, I mean, this is the 2-point correlation. So it's theta times psi plus, for example. So it has this characteristic hump shape. And what's plotted is the expected error bars at some at the fiducial value of this feedback that we expect from LSST y1 cross y1. And then different lines show how exactly this curve is if you change the feedback strength. And I think like in here, you can see that these are 2 halo scales. So in here, if you have higher feedback, it will push the gas out of the halo, but it won't change the total mass once you smooth out at really high arc minute rate. So you see the impact of feedback is much less, but on small scales, you are now probing approximately 1 halo or transition regime, and you can see that that's where you see the impact of feedback much more.
Great, thank you.
Thanks. And unless you had a question?
Yes. Could you go back to your cosmological constraints from shear plus TSZ? Yeah, here. So could you explain why? So when we look at the parameter for the gas ejection, it seems like from what you were saying, the shear cross TSZ should be kind of driving the constraints. But when you combine, it seems like it's actually going towards what shear was measuring. So could you explain why it's not driving that constraint?
Yeah, it's because I think like the shear cross TSD has very high degeneracy of this parameter with cosmology. So like cosmology is, you can see, right, like the omega matter S8 plane is almost not constrained at all. So I think like what you're seeing here is effectively some sort of projection effect in the marginalized constraints. But I think like once you analyze it jointly, this is like, I think where shear cross TSD also prefers this parameter to be, because I think the cosmology is much more tightly constrained per shear 2-point.
Okay.
Okay. I don't see any more raised hands. There is one. Yeah, let's have one final question.
Do you still use any scale cuts in your full result, or are you using all data from DES?
You know, this is using everything from 2.5 to 250 arguments.
Okay. Okay, let's thank all our speakers again. We will now break for lunch, and we will reconvene in an hour and 15 minutes for the panel discussion.